Hey, grade 8's case section, what the, this isn't section 11.1, it's 11.2. Okay, so outcomes of independent events. So we're looking at a different way that we can find the total number of outcomes that there will be. Not necessarily finding probabilities, but just how many outcomes. So let's look at this example. Determine the total number of outcomes from two events. So Carrie, this is Carrie right here. She flips a coin and she rolls. So here's the coin. That's a coin. And here is a standard six-sided die. And how many possible outcomes are there with those two events? So we could find these outcomes using our, let's do a tree diagram. So she could get a heads or a tails with the coin. And then she could flip the heads, and then she could get a 1, a 2, a 3, a 4, a 5, or a 6. Or she could flip the tails and then get a 1, a 2, 3, a 4, a 5, or a 6. And now we can see, we can write it all out if we want to. Heads and 1, heads and 2, heads and 3, heads and 4, and so on. And we can write it all out, and we can see all of our possible outcomes, which is really handy for when you're looking for specific ones. So writing out your sample space is often going to be useful sometimes. Although we're going to be learning some new tricks that make it less necessary. Okay, and so we can count, and we have 6 at the top here and 6 at the bottom, so we have 12 total outcomes. We have 12 possible outcomes looking at combinations of those two events. Now, what you can maybe notice is that there are 2 possible outcomes with the coin and 6 possible outcomes with the dice. And what does 2 multiplied by 6 equal? That equals 12. So we were able to take the total possible outcomes from the one event, multiply it by the total possible outcomes from the next event, and we get the total number of possible outcomes, which is a bit easier than doing all this work if you're just trying to find how many outcomes there are. Okay, so what if there's 3 or more events? So a coin is flipped, a spinner divided into 3 equal regions is spun, and a 4-sided die numbered 1, 2, 3, 4 is rolled. So how many possible outcomes are there? Again, we could use our tree diagram. We get heads or tails, and then from each of those you could get A, B, or C on the spinner. And then after that, there's a 4-sided die, and so you could get 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, and you have to do all this and make it hard to see because I'm messy, and it just gets a little bit, you can show it with a tree diagram. And we could write out all of our sample space and see how many there are and see, okay, well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24 possible outcomes, because each one of those numbers shows the end of a route through this tree. So there's 24 possible outcomes. But what you can also do, which makes it a little bit easier, if we're just finding the number of outcomes, to say, okay, well, there's 2 outcomes here, there's 3 outcomes here, there's 4 outcomes here. And we can multiply together the number of outcomes. 2 times 3 is 6. 6 times 4 is 24. So we know there's 24 possible outcomes. So just by using this little trick of being able to multiply each of the possible outcomes from each event, we can find the total number of outcomes of those combined events very easily without having to draw our big tree diagram. So B, why could you not easily represent the sample space for this probability experiment with a table? Well, a table has when we're drawing it on a piece of paper, it only has two sides. And so you can show one event down here, you can show another event up here, but showing a third event, we don't have another third direction we can show it to fill it in. You'd actually have to have a 3D table with, you know, another one going a different way and then filling in like the volume of a box or whatever to show a third event. So tables are great for when you only have two events. Don't work very well for when you have more than two. Okay, wow, this is way too big. Can I like, oops. To make this smaller, sorry. Can I move this too? Okay, I guess. Oh no. Let's see. Oh, bless me. Okay, I'll just ignore that table that I was going to try to use down there. I'll just do it to the side. So a cafe offers 4 types of sandwiches: egg salad, tuna, ham, or turkey, on one of 3 types of bread: white, rye, or whole. So use a table to determine the number of sandwich combinations offered by the cafe. So black. Okay, so you have the type of sandwich, and you could have egg salad, you could have tuna, you could have ham, or you could have turkey. I already have a T, so I'm going to say TY, turkey. Okay, those are the 4 different types of sandwiches you could have. You also have a type of bread you could have that sandwich on, and oops, those types are white, rye, or whole wheat, WW. Okay, and now we can make our table, and now we can fill these in. You could have your white bread, egg salad on white bread. You have white bread with tuna. You could have white bread with ham, or you could have white bread with turkey, or you could have rye bread with egg, rye bread with tuna, rye bread with ham, rye bread with turkey, or you could have whole wheat bread with an egg salad on it, whole wheat with tuna, whole wheat with ham, or whole wheat with turkey. Okay, and here's all possible outcomes. So now we can see how many there are. We can count them: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There we did it. There's 12 different sandwich combinations offered by the cafe. So we answered A. Well, B, let's check the answer using a different strategy. Well, we just learned that we can just multiply the possible choices from each. And so we had 4 types of sandwich multiplied by the 3 types of bread is also equal to 12. So there's 12 sandwich combinations. We can just take the 4 choices for type of sandwich multiplied by the 3 choices of bread. You get your answer. Okay. So that's it. That's the main idea here. So the key idea being, we can find the total possible outcomes by making our table or drawing our tree diagram, which is shown here with a coin and a 5 space spinner. And we can see that there are 10 possible outcomes for flipping a coin and then spinning the spinner. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Or 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so there's 10 possible outcomes. But an easier trick is that you can take the number of possible outcomes for each event and multiply them together. Okay, so the total number of possible outcomes can also be determined by multiplying the number of possible outcomes for each event. Just a little trick. So this shows us that probability is crazy. So I maybe have talked about this with some of you before, but how many possible arrangements could a deck of cards have? So A deck of cards has 52 cards. Okay, so how many possible, if you were to shuffle a deck of cards, how many different cards could be the first card on top of the deck? Well, there's 52 possible cards, so you could have 52 options for that first card. Well, once that first card is taken out of there, how many different cards could there possibly be at the second space on the deck, the second card? Well, there'd be 51 cards left. And the third card, there's 50 choices. Oops, 50 choices for what the third card could be, multiplied by the 49 possible options for what the fourth card could be, multiplied by the 48 for the fifth card, multiplied by 47 for the sixth card. And we just keep doing this. This is actually called a factorial. And we keep going all the way down to 1 times by 46, times by 45, times by 44. Now you could do this. You'll also notice that on some calculators, there's going to be a exclamation button, and that's what this is doing. So 52, 52, we call it, it looks like you're just yelling 52. That's called 52 factorial. Now, just so you know, what I'm talking about here is not part of the curriculum at all. I just think it's fascinating. And 52 factorial, so 52 times 51 times 50 times 49 times 48, all the way down to 1. Let me see on my calculator here. What does that equal to? That is equal to, this is an insane number, 8.065 times by 10 to the 67. So that is 8 followed by, times 10 to the 67 means followed by 67 zeros. So 8, and so this is a huge, huge number, like way, way bigger than trillions. And then 67 zeros, right? So they just would, there'd be 67. Once I did 67 of these zeros, that would be how big this number is. Which means that there's that many different possible arrangements of a deck of cards. Okay, and this is what's crazy, is that there is never, it's very unlikely that ever in the history of humanity, there has been 2 decks of cards that have been well shuffled and been in the exact same order. Okay, in fact, if if there were 7 billion people on Earth, and if there had been 7 billion people on Earth for the last 100 billion years, and every one of those 7 billion people for the last 100 billion years, every second had been shuffling a deck of cards every second, we would still, and up until this point, we would still be not even close to having this number, have shuffled this number of possible arrangements of cards. If everyone had been different, we wouldn't have even come close. You would in fact need about 100 billion Earths with 7 billion people that have been around for 100 billion years, shuffling one deck every second, and even then you will actually not even come close. So it is an insane number. Sort of amazing that, yeah, there's likely, statistically, if a deck of cards has been shuffled well, and shuffled means doing it in a random way, there's never been 2 that have been in the same order. It's very, very unlikely, actually. So there's some cool math for you. Anyways, you just have to multiply possible outcomes. Oh, I'm trying to go back. It's not working. Multiply possible outcomes, find the total possible number of outcomes. That is it.